Hello, this is Jack Hicks, and this is my submission for the Physics 2211 Lab 1 Constant Velocity. The two main objectives of the lab were to observe and analyze an object moving with a constant speed without changing direction, and then to create a computational model that predicts the position of the object based on the observed data and fundamental physics principles. After this, we could compare the observed position with the predicted position by overlaying the values on a single graph of position versus time, and then discuss the similarities and differences in the two values. The main ideas in this experiment had to do with velocity, Newton's first law, and Newton's second law. Velocity being the change in position of an object with respect to the change in time, which is constant when there is no net force acting on the object. Now the net force could be zero, meaning that there are no forces, or that all the forces that do interact cancel each other out. Newton's first law states that an object in motion stays in motion unless acted upon by an outside force, while his second law states that an object's change in velocity is determined by the amount of force applied divided by the mass of the object multiplied by the change in time, which is seen in the velocity update equation below, which is subsequently applied to the position update equation even farther below that. In doing the lab, a roll of tape was rolled from the right side of the table to the left side of the table being in the negative x direction and the right side being in the positive x direction. The system was the roll of tape, while the surroundings were essentially everything else. And by comparing the observed values versus the predicted values, it was found that the magnitude of the position change in the observed values was actually greater than that of the predicted values. That is, the predicted values went less far than the observed values did in the negative x direction. Now, it must be noted that GlowScript was used to code because it allowed for efficient and easy computations regarding velocity and position updates. But what computational models are we actually using? The model used was of Newton's second law, which was previously discussed, so I won't go into it too much. But using GlowScript, a while loop was used to continuously update the force, velocity, and then position of an object over specified time intervals, which would get us the computational model. Now, force was constant, and thus so was velocity, since we assumed no friction nor air resistance, and then essentially only position was updated. Now, to do this, we had some known values, which were both observational and applied to our model. The mass of the tape roll, the initial velocity, and the initial position, which are listed here. So getting into the actual experiment, here's a video of the experiment actually being done. And here's the data given by analyzing the video using the Tracker app, having the calibration stick, the axes, and the individual x and t values labeled, along with a couple graphs on the side. This will be used later. After this was the process of taking data we had and making predictions about the motion we just observed. Here is a picture of the code used with the relevant parts highlighted. The mass, position, and velocity of the ball are initially found using observed data and plugged into this while loop over here. The while loop has a force of 0, since we're assuming no friction or air resistance. The velocity is constant, being velocity plus a 0 vector. The 0 vector doesn't even need to be there. And the position is simply the position plus the velocity times delta t. Delta t being 0.033333, because that is the time interval the tracker used. Doing this again and again and again until delta t was equal to our final t value in the tracker, so we could have a comparable model. Here are images of the data that the model gave us, the visualization having the ball starting on the right and going to the left, the position versus time graph with a constant slope being shown here as a constant velocity. Now when we compare both observed and predicted data, this is what we get. So here we can see that both sets of data start at the same point and then slowly grow apart as time increases. The observed position of x decreases faster than the predicted position. Now both sets of data, while having different slopes, are both showing constant velocity. Now error in this, why the predicted and the observed don't match up, could be because the table was not perfectly even perhaps, and thus the observed position was actually farther than it would be predicted on a flat surface, or there could be user error in how the video was shot or analyzed. So some additional questions were, what if the axes were flipped, and simply put, negative will become positive and vice versa? Nothing would change except how we view the problem, because the magnitude of displacement would not change and all sign values would change, so it is an arbitrary change. Now, is it possible to count the forces on an object that add up to zero? Simply put, no. Some you can, like weight or the force of contact from the table, but many forces are individual, such as very small gravitational influences from me or the people around me or anything like that. They're negligible, but they still occur, and you really can't count all of them. So, yeah, and that's it. Thank you so much for listening.